Actually, we have two, not one, but two important results. One is the famous and celebrated Carathéodory extension theorem, and the other is the Hahn extension theorem. Let's start with the first. According to the Carathéodory theorem, actually the Carathéodory extension theorem claims two things. The one is the family of subsets for which the adding of property holds is a sigma algebra. This is an important result. So we can form a sigma algebra on which the adding of property holds, and to which and this is the second half of the theorem. To this sigma algebra, the measure defined on the algebra can be extended. So plainly put, we can define a measure on an algebra. We can find a sigma algebra for which the adding of property holds. This is a sigma algebra, and to this we can extend the measure that we defined for the algebra. So according to the Carathéodory theorem, it is possible for us to define a measure on an algebra and to extend it to a sigma algebra that contains those subsets for which the adding of property holds. But there is a problem. The Carathéodory theorem leaves open the possibility that there may be more than one extension of the measure defined on the algebra. In other words, according to the Carathéodory theorem, the extension may not be unique, and uniqueness is a great thing. So we want to have a unique extension to the sigma algebra. So to this end, we need the second result. This is the Hahn extension theorem. But to state the Hahn extension theorem, we need a definition. The definition of measures being sigma finite. So we need to make a distinction. Sorry. We need to make a distinction between measures being finite and sigma finite. The finite version is the simplest because a measure is finite if it is not infinite. So if we have a measure which doesn't take on positive infinity for any element in the sigma algebra, it is finite. Sigma finite measures are different because a measure to be sigma finite, we must have a series of subsets, the union of which is the state space, and for which, for the sets, the measure must be finite. It doesn't exclude this definition doesn't exclude the possibility that the measure is not finite. What it states is that there is a series of subsets, the union of which is the state space, and for which, for the subsets, the measure is finite. So we can say that being finite is the stronger requirement, because a measure which is finite, it is necessarily sigma finite, but a measure can be sigma finite while it takes on infinity for certain elements in the sigma algebra. So if the measure we defined on the algebra is sigma finite, according to the Hahn extension theorem, the extension is unique. So the Carathéodory extension theorem and the Hahn extension theorem they ensure that there is an extension from the algebra to the sigma algebra, and the extension is unique.
This is exercise 7.7 on the basis of Bartol's lemma 9.3. In this exercise, we are supposed to show that length is a measure on the real line. Here, I don't want to provide the complete proof. This is just a sketch. All I want to do is to show the basic idea underlying the complete proof. By length of an interval, we mean this difference. So actually, this is the difference of two real numbers. The idea underlying the proof that length is a measure is very simple. We have the real line, and we have a closed interval in this form, and we divide this interval into a series of disjunct subsets, disjunct intervals in this form. And by playing on this division, we can show that the length of the entire interval can be written in two ways. One is the sum of the length of the individual intervals, which is equal to the length of the sum of the individual intervals. That's the main idea underlying this problem.
The next question to answer is what functions facilitate the discussion about the expression regarding the expected value of a function. The answer, we need measurable functions. So first, let's define measurable functions. If we have a measurable space, a real valued function mapping from the state space, let's call it S the state space, mapping from the state space to the real line is measurable with respect to the sigma algebra if the inverse image is in the sigma algebra. The inverse image of an interval, the inverse image of a set is in the sigma algebra. So formally speaking, the set to which the function is smaller than or equal to a real number is in the sigma algebra, then the function is measurable. In other words, we can say that the inverse image of an interval belongs, if the inverse image of an interval belongs to the sigma algebra, then the function is measurable. If the measurable space is a probability space, then the function is called a random variable, and the expectation operator simply describes the expected value of this random variable. It's an exercise, not too demanding an exercise, to show that actually we have four equivalent definitions of measurable functions, all of which are built on the same idea. The inverse image of an interval must be in the sigma algebra. Okay, so this is the formal description, formal definition of measurable functions. How to find measurable functions? This is the next question. We have good news because it's not too difficult to find measurable functions. It's not an exaggeration to say that it's quite easy to find measurable functions. For instance, any monotone or continuous function, real valued function, is measurable with respect to the borrower set. So it means that the inverse image of an interval is always an interval, so it's in the Borel algebra. So any monotone or continuous, it is very useful. Any monotone or continuous function is measurable with respect to the Borel sets. How can we show, how can we prove that function is measurable? We have two available strategies. One is the direct attack. In this strategy, we get the function, we use its properties and the properties of the related sigma algebra, and we show that the function is measurable. This is the direct attack. The other strategy leads through simple functions. In this case, we trace back the function we are interested in. We trace back the function to simple but measurable functions. So we show that this function can be described as a simple function in a way, and as the simple functions are measurable, then our function must also be measurable. So what is a simple function? We can define simple functions in two steps. First of all, we need an elementary simple function. This is not an official term, but let's use this for now. So a very simple function is the indicator function. If we have a measurable space, the indicator function takes an indicator function takes on two values, 1 and 0. We have a subset of the state space, and if S falls into A, then the indicator function is 1. If S doesn't fall into A, subset A, it's 0. So once again, the indicator function takes on two values, 1 and 0. This is very useful because on any measurable space we can define simple functions by the weighted average of indicator functions. Okay, so a simple function, in other words, is a step function because it takes on, a simple function takes on a finite number of values. Okay, so this is the reason why we call it a step function. A simple function can be described as the weighted average of not weighted average, a sum of indicator functions, and if the subsets on which the indicator function is defined, they are disjunct, and if the real numbers, the weights, are distinct, then the simple function is in a standard representation. This is going to be very important to us in the later discussion. So we have simple functions which can be described in a standard representation in which the state space is divided into into a series of disjunct subsets over which we have distinct real numbers, and the simple function, the step function, is simply the sum of the indicator function weighted by the real numbers over the state space. We have two important results. One of them is theorem 7.4, according to which pointwise convergence preserves measurability. Simply put, if we have a measurable space and if we have a series of measurable functions over this measurable space, and the measurable functions converge pointwise to a function, then the limit function is also measurable. it can be formally proven, and the proof is very nice, so I suggest we should go over, in an informal way, we should go over the proof, and to this end I have this small figure. So let's see the sketch of the formal proof. The proof can be completed in I guess 2 steps, and to this end we need to define some functions. You can read the definitions of these functions. The point is the measurability of functions are based on the measurability of the functions in the series. So in the second step, as you can see, we define 2 functions which are key in the proof of the theorem according to which pointwise convergence preserves measurability, because for every s we can define the 2 f functions, f tilde and f capital tilde, and starting from different n we have different sets of numbers for every single s. So for every single s, these definitions define sets of which we can find the supremum and the infimum, and you can see that the measurability of f tilde and f capital tilde is based on the measurability of the functions in the series, and given the fact that these functions in the series converge pointwise to a function, f tilde and f capital tilde are equal, so the measurability of the limit function comes from the measurability of the functions in the series. So this is simple as that. The next theorem is theorem 7.5, approximation of measurable functions by simple functions. This is a very useful result, and this is one of the theorems that establish the very favorable, very beneficial convergence properties of the Lebesgue integral, which we are about to deal with in a couple of slides. If we have a measurable space, and if there is a function which is measurable with respect to the sigma algebra, then there is a sequence of measurable simple functions, so that this series of measurable simple functions converges pointwise to this function. And if this function is non-negative, then this sequence can be chosen so that all the functions, simple functions in the series, are non-negative. And if the function, the limit function, is bounded, then the convergence is uniform. We can see the proof, because it's very simple. We can see the proof for non-negative f.
Exercise 7.10 can be easily solved by having a look at Bartol's examples 2.5 C and D. Here we need to show that if we move on the real line, then any function which is continuous or monotone is Borel measurable. So if, formally, let's put it formally, if the state space is the real line, and the related sigma algebra is the one-dimension Borel algebra, then for any real function which is continuous we have a measurable, a Borel measurable function. F is Borel measurable. Here the only thing we need to do is to go back to the formal definition of measurable functions. Let's take this set, those numbers, the set of those numbers to which this inequality holds for the function. So this is the inverse image of the set. In other words, this is the inverse image of the set where fx is higher than alpha. The inverse image is an open set. So we have an open set on the real line, and the open set, the inverse image, this open set, which is the inverse image, is in the Borel algebra, so f is Borel measurable. So we have just proven that a continuous function, any continuous function, is Borel measurable. We can do the same for monotone functions. So if f is a monotone increasing, for monotone decreasing functions it's the same, the proof is the same, monotone increasing function, we will do the same as previously. We have this set, those real numbers for which the function is higher than alpha. The inverse image of this relation is a half line. The inverse image is a half line which is in the Borel algebra. So the inverse image of the set that fx is higher than alpha is an open set. The inverse image of a half open set is a half open set which is in the Borel algebra. So a monotone increasing function is Borel measurable. This is what we needed to show.
We are approaching the finish line, but still we have a lot to do. Our ultimate goal with this discussion is to understand the expected value of a function. To describe the expected value of a function, I think it's quite clear that we need a measure space, which is a triple of a set, a sigma algebra, and a measure, and a measurable function. So the value. So if we insist on the example of the Bellman equation to describe the expected value of the value function v must be measurable. The final step to take is to introduce integration, because the expected value of the function, you can see, is the integral of the function with respect to the chosen measure. So if we want to calculate, describe the expected value of the function, this function must be integrable with respect to the chosen measure. At this point we have two families of functions, two spaces of functions. One is the more general, this is the space of measurable real-valued functions, and the other is a narrower space. This is the non-negative, measurable non-negative real-valued functions. We will establish integration on the latter. So first, as a first step, we will establish integration for non-negative measurable real-valued functions, and as a next step, we will extend integration to the more general set, more general space of measurable real-valued functions. The strategy which we are going to follow is very similar to the case of measurability. As you may remember, we can prove measurability of functions by the measurability of simple functions. So we can, in many cases, we can trace back the measurability of functions to the measurability of simple functions, and this is what we are going to do in the case of integration too. We have functions, the very useful simple functions, which are integrable, and if we can find a way by which we can trace back the functions we are interested in to these simple functions, we can ensure integrability by the integrability of simple functions. You can see that if we have a simple function in the usual standard representation, it's quite easy to calculate the integral of a simple function. You can see it's the weighted average of the measure of the disjunct sets into which the state space, the set, is divided into which the state space is divided. You can see that measures play a key role in integration, because the integral of the simple function is no more than the weighted average of the measures of the disjunct set. So this is the reason why we had an extended discussion about measures. Before moving on, let's have a few words about two different frameworks or concepts of integral. One is the more commonly known Riemann integral, and the other is the less known Lebesgue integral. Riemann integral is widely taught in real analysis, so I think in your analysis classes, Riemann integral is the integral you learned. The Lebesgue integral is perhaps it's a bit more difficult, it may be challenging, but in return the Lebesgue integral has more favorable or beneficial characteristics. It's more flexible. It has some very beneficial convergence properties, and as another instance of flexibility, there are functions which cannot be integrated in the Riemann integral framework, but they can still be integrated in the Lebesgue framework. Luckily, when a function can be integrated in both of these frameworks, the integrals are the same. So in the simplest cases, the Riemann integral and the Lebesgue integral are the same. But sometimes we cannot integrate a function in the Riemann framework, but we can integrate it in the Lebesgue framework, and there are functions which cannot be integrated not even in the Lebesgue framework. Okay, so this was just a preliminary introductory remark to the Lebesgue integral, because this is the framework we are going to use in this discussion. Let's start with some useful facts. If we multiply a simple function with a constant, a real constant, then the integral of this multiplied function is the integral of the simple function multiplied by the constant, and the integral of the sum of two simple functions is simply the sum of the integrals of the individual functions. The next useful fact is the first step we take towards defining probability measures. You can see that if we integrate a simple function over a set, then it's a measure. So this is the first step towards the probability measure, because this is exactly what we are going to do with the density function. We integrate the density function over a subset of the state space, and it's gonna be a probability measure. And this is the first step towards this formulation. And I guess the last point is the most important one, because here you can see how can we trace the integral of a function back to the integral of simple functions if we have simple functions which are not greater than the function we are interested in. The integral of the function is the supremum of the integral of these simple functions, where the supremum is extended over all the simple functions which are not greater than the function we want to integrate. So we practically and plainly put, we can find many simple functions which are not higher than the function we are interested in, and we can find the one in the set of integrals of these simple functions which is the supremum of the set, and this supremum is gonna be the integral of the function. Some further useful facts. The integral is monotone in a twofold sense. If we have two functions, f and g, in the space of non-negative, real-valued, measurable functions, so that f is not higher than g, then the integral of f is not higher than the integral of g. This is one sense, and the other sense in which the integral is monotone. If we have a function in the same space, and if we have two sets in the sigma algebra, and if one of the sets is the subset of the other, then integrating the same function over the smaller set leads to a not greater integral than integrating the same function over the larger set. Okay, and on this basis we can state a very useful result, a very useful theorem, very extensively used theorem. This is the Monotone Convergence Theorem, which is very useful because this is one of the theorems that establish the convergence properties of the Lebesgue integral. We are still in the space of non-negative real-valued measurable functions, and we have a series of functions in this space, a monotone increasing sequence of functions that converges pointwise to a function. Then, according to the monotone convergence theorem, the integral of the limit function is the limit of the integrals of the functions in the sequence. This is a very useful result. So if we know, practically speaking, if we know that a function is the limit of a series of monotone increasing functions, then the integral of the function is the same as the limit of the integrals of the functions in the series. If convergence is mu almost everywhere, by which we mean that convergence doesn't necessarily hold over the whole state space. It may be the case that convergence holds only for a smaller subset of the state space. We have the same result. A consequence of the monotone convergence theorem is that we have the same rules for any functions in the space of non-negative, real-valued, measurable functions than we had for measurable simple functions. For instance, the integral of the sum of functions in M plus is the sum of the integrals of the individual functions. We skip the proof, but the proof is very simple. All we need to do is to set the function f and g, functions f and g as the limits of sequences in M plus, and the result follows immediately. Here we can take a very important step, because as I have just mentioned, in the case of simple functions, by integration we can define a probability measure. We have already taken the first step. We showed that by integrating a simple function over a set, we can define a measure. The same is true of not simple functions, functions in M plus. So by integrating a function in the space of by integrating a non-negative measurable function over a set, we can define a measure. And please note that the density function is a non-negative, real-valued, measurable function. So by integrating the density function, we can define a measure which is the probability measure, which we are going to use extensively, very extensively, in later discussions. And last but not least, I would say this is my favorite theorem in measure theory and integration. If we have a non-negative measurable real function, we can say that this function is 0 mu almost everywhere on S, if and only if the integral is 0. The proof is very nice, so I will show you the sketch of the proof. The proof is about showing that fs equals 0 mu almost everywhere implies that the integral is 0, and the opposite. So the integral is 0 implies that the function is 0 mu almost everywhere. So this is what we are going to do now, because the proof is so nice. So I suggest we should stop for a minute. The proof is very nice, and it's built on a very simple idea. Just like previously, I don't want to show you the whole and complete proof. I just want to show you the main idea underlying the proof. If a measurable function is 0 mu almost everywhere, it means that we can divide the state space into two sections. On one section, the function is positive. This is set A, and this is the set the measure of which is 0. And on the complement of this set, this section, the function is 0. Where the function is 0, the integral is simple, because if a function is 0, then its integral is also 0. So given the fact that the function is 0 mu almost everywhere, we can know that where the function is 0, its integral is also 0. As a next step, we need to pay attention to that section of the state space where the function is not zero. Here, the function is positive, and it can be forced under a simple function. You can see we use the indicator function over the set A, and we can integrate this simple function with respect to the measure over set A. But over set A, the integral must be zero because the measure is zero on set A. So altogether, given the fact that the function is zero mu almost everywhere, its integral is zero. Because where the function is zero, once again, where the function is zero, its integral is zero. And where the function is not zero, we use the fact that on that set, on that section of the state space, the measure is zero, and the integral of the function cannot be greater than the integral of the simple function, and the integral of the simple function is traced back to the measure, which is zero over set A. So altogether, the integral of the function is zero. That's all. It's very nice and very simple. Having done all this, now we can try to interpret, to understand the integration of measurable real-valued functions in general. So at this point, we are leaving the space of non-negative real-valued measurable functions for the space of real-valued measurable functions in general. I have a figure which is very simple, but I hope it's instructive. In the figure, we can see a general real-valued measurable function that takes on negative values for a subset of the space, the state space. The idea is simple. So integrating such a function can be simple. It is simple because we can reduce the problem to the integration of non-negative real-valued functions. The only thing to do is to find that section of the state space on which the function takes on negative values, and we need to take the absolute value of the function over this subset of the state space. The result is a function that takes on positive values only, and on this basis we can define the space of integrable functions. These are the functions, the positive and negative sections of which have finite integrals. In this slide, I try to summarize some basic results starting with the content of the previous slide. Here you can see how to formally divide an integrable function into a positive and a negative part or section. And you can see also that the integral of the function is simply the difference of the integral of the positive part and the integral of the negative part for the whole state space and for smaller subsets of the state space. This is a very useful fact. On this basis, you can see that we have the same rules for integrable functions. So once again, the integral of the sum of integrable functions is simply the sum of the integrals of the individual functions. The most important thing, I guess, in this slide is the Lebesgue Dominated Convergence Theorem. Instead of putting formally the whole thing, I just want to highlight that this is the same convergence theorem, the monotone convergence theorem we have already covered for functions in the case of which convergence is only mu almost everywhere. So if we have a series of functions that converge to a function mu almost everywhere, we have the same convergence of the integrals, just like in the case of the monotone convergence theorem. This is a very useful fact too. This is the final topic and the final slide for the lecture. Let's talk a bit about product spaces. A product space is the Cartesian product of measurable spaces. The first question to answer, why we need product spaces. The answer is simple, because in a stochastic model we have more than one state variables. One state variable is the so-called endogenous state variable. This is the state variable that is under the control of the agent. So by its decisions, through its decisions, the agent affects the dynamics of the endogenous state variable. This is the reason why it is endogenous. The other state variable is the exogenous state variable, like a shock to the return function. This is not under the control of the agent, but the exogenous state variable affects the outcome of the decisions. So simply put, in a very, very elementary framework of a stochastic dynamic programming model, the agent is supposed to make a decision about the endogenous state variable, for instance, capital stock next period, while the outcome of the decision, the return, is affected by the stochastic shock next period, but the agent doesn't know the value of the exogenous state variable. The agent has no more than an expected value, so the agent is supposed to make the decision regarding the endogenous state next period on the basis of the expected value of the exogenous state variable next period. So this is a very, very elementary framework for the problem in a stochastic dynamic programming model. The point is that we move in a rectangle. So when we have an endogenous state variable and an exogenous state variable, the state is a point in a two-dimensional rectangle. So the exogenous state variable moves in its own state space. The endogenous state variable moves in its own space, and the state as such moves in the rectangle, the edge of which one of the edges belongs to the endogenous state variable. This is the state space for the endogenous state variable, and the other edge of the rectangle comes from the state space of the exogenous state variable. And we want to describe the dynamics of the state. So the problem is very similar. We need a probability measure by which we can describe the probabilities of the event that the state, including the endogenous and the exogenous state variables, fall into a subset of the state space. So this is not too complicated, and in the applications later, in the later lectures, in the subsequent lectures, we will do this in practice. So for now, it's enough to lay down the foundations. It's not too complicated, and we will have time to do it in practice. So first of all, we need a definition, the measurable rectangle, the definition of measurable rectangles. This is a set in the space called Z. This is literally a rectangle with two edges, edge A and edge B, and both of the edges belong to the sigma algebras of the state spaces of the endogenous and the exogenous state variables. So the problem is similar to the previous cases. We need an appropriate sigma algebra for measurable rectangles. We will do this in two steps. First, we define a measure for measurable rectangles. Then we extend it to the algebra of the finite unions of measurable rectangles. And in the second step, we extend it to the sigma algebra of measurable rectangles, which is the Cartesian product of the measurable spaces of the variables. So first we define a measure for measurable rectangles. If we have a sequence of disjunct rectangles, so that the union of these rectangles is in the set of measurable rectangles. So this is very simple. We need a series of rectangles, the union of which is also a measurable rectangle. Then you can see that the measure is supposed to abide by the simple adding up property, and the fact that the family of all finite unions of measurable rectangles is an algebra, we can use the fact that all the elements in E can be described as a finite union of disjunct rectangles. So the measure that we defined for measurable rectangles can be used in the algebra E of all finite unions of measurable rectangles. So as a first step, now we have a measure that can be applied to the algebra of finite unions of measurable rectangles. This was the first step. And in the next step, thanks to the Carathéodory and Hahn extension theorems, this measure can be extended to the sigma algebra of measurable rectangles, which is very intuitively is the Cartesian product of the measurable spaces of the state variables. Okay, so it was this very, very long lecture about integration and measure theory. I don't think it was a complete picture, but hopefully I could cover the most important topics and problems. So hopefully you will find this introduction useful to an extent. This was not the last time we were trying to deal with these problems. In the later lectures and in the later practical sessions, we will have time to apply these theories in practice. See you soon.